So on this slide we want to describe regular functions on an open subset of an affine algebraic set. So let us write this down. So you have regular functions on an open subset, say U. So regular functions on an open subset U of an affine algebraic set. So you denote affine algebraic set by X. So we want to define regular functions on open sets U. So in the slide of quasi-compactness we described what these open subsets were. Now notice that we already know what the ring of regular functions is on entire affine algebraic set. Yeah, so on the entire affine algebraic set we just have polynomials. Yeah, these are elements of this ring. So since it is subset of an, we write k x1 to xn modulo the ideal associated with the algebraic set X. Okay, so now we want to define regular functions on open subsets. So let us again draw open subsets. This is set X. The open subset is just this affine algebraic set X, which I have just drawn like a circle with some finite number of points missing. So this is open set U. So there are 4 points missing. Yeah, these missing points I am drawing in red. So these missing points correspond to some polynomial, say S, which is cutting X. Yeah, that is how so those points are missing. So just 4 points are missing out of X and we get U. So regular function of U is a function, obviously it takes U to closed field K. So it's nothing but a function f from U to K. So K is closed such that for every point P in U, P in U, there is an open subset. Yeah, there is a neighborhood around this point P, and this neighborhood is contained in U. So there is an open subset V. This point P is contained in V. V is contained in U, on which we define f equals to G over H. Yeah, with G and H, yeah, with G and H, obviously H is not 0 on small set V, and G and H are polynomials. Yes, H is not 0 on only a small neighborhood V. So we insist that the definition is local. That is, so you have this point P, which I have just drawn in blue, and we have this set V, which I am going to draw in green. So on this set, H does not vanish, but H could vanish at multiple other points in U. So H does not vanish in this green marked set, but it could vanish at other points. Say H vanishes, so I'm going to mark points where H vanishes. Yeah. So H could vanish here, 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 all these points in orange. Yeah, here. So, but it does not vanish in the green portion. That is it. So H could vanish at multiple points of U. Where it does not vanish is at the point P and its small neighborhood. So the definition is extremely local. So another definition. So such functions which we just defined above, they are called the ring of regular functions, and we will write them like this. Okay. Now coming on to an important theorem. Now see, you have these fractions here, and whereas OX is just polynomials. So we need to make these two things consistent. Definition F equals to G over H and the polynomials. So if instead of open sets you start considering the entire space, so instead of open set you march on towards the open space, yeah, you end up getting polynomials again. Yeah, so let us write this down. This is a theorem whose proof we will cover in the next slide. So we have functions like G over H and U subset of X. So they just become polynomials when we go from U to the larger set X. So let us write this down. Just become polynomials when we grow from U to larger set X. So let us now cover some examples. So the first example is you have you set your set U as affine line minus 0. Yeah, and X is the affine line and our regular function is 1 by X. Yeah, so notice that it is not defined on X, yeah, because it is not defined on 0. So the theorem is not applicable here, yeah, because the function is not even defined. If the function was defined, then it will become a polynomial. That is what the theorem means. So now we want to describe function f as g over h. Now this is not unique. Yeah, you can multiply numerator and denominator by m, where m could vanish on certain points of u, but it does not vanish on the neighborhood of the point p where we evaluate the function. So it does not vanish on set neighborhood of p, which is we are denoting by v. You could also write it like this, where L vanishes on this algebraic set X. So L is 0 on the entire set X, and therefore it is also 0 on U, because U is an open subset of X. Now a couple of remarks we want to make with regards to the theorem. So remark is, so consider this, 1 over x square plus 1 on real numbers. Yeah, now this is defined on entire real numbers and there is no polynomial which corresponds to it. Now does this mean the theorem is incorrect? The theorem is not incorrect precisely because the theorem applies only for k closed, and here R is not closed. Now obviously if so R is not closed there, so the theorem is not applicable. Now if you were working on complex numbers, this would split, yeah, as x square plus 1 would split. Now this is not even defined on complex numbers, yeah, because of the poles at I and minus I. So since it is not defined on complex numbers, we cannot find the polynomial. So the theorem is not applicable. So the theorem is applicable. So the gist of the story is the theorem is applicable only if g by h is defined on the set X. So let us write this down. Not defined at minus I or iota minus iota, and theorem therefore does not apply. So let us now prove the theorem. So the theorem is that on set U, a smaller set U, we had rational functions, and now on a bigger set X, these rational functions become polynomials. So let us write this down. So we have on the affine algebraic set X, we end up having polynomials, and on smaller sets U which were open, we had rational functions. Yeah, so proof is, so cover X by some open sets. Yeah, so we need to define how these open sets come about. So we will do that in a minute. But on each open set U alpha, you write the function f as G alpha by H alpha, where both G and H alpha belong to the polynomial ring. Yeah, so let us write this down. Obviously H alpha is not 0 on U alpha. So H alpha is not 0 on U alpha. Okay, so now let us define an open set. So choose a polynomial S, which, yeah, so let us do S element of k x1 to xn. Now you attach a set US. I'm writing S, this should be US. That is all those points of affine algebraic set X where this polynomial Sx does not vanish. So US is open in affine algebraic set X. So let us draw a figure to make our ideas more concrete and clear. So US is open in X. So first we will draw X as a circle. Yeah, so now notice this is a polynomial S. Yeah, so what is US? So US is precisely those points where S is non-zero. So that is X minus 4 points where the polynomial figure cuts X, because what I have drawn X with S with color brown is nothing but the equation of the polynomial Sx equals to 0. So X minus those 4 points in brown is what US is. That is precisely those points where the polynomial does not vanish. So yeah, so it vanishes only on 4 points, and on the rest of the points the polynomial does not vanish. So on US alpha, you can write f as G alpha over H alpha. Now we multiply both numerator and denominator by S alpha, because S alpha does not vanish on entire of US alpha. Yeah, so S alpha does not vanish on US alpha. Neither does H alpha vanish. So we have neither S alpha vanishes nor H alpha vanishes on US alpha, I should say there. Yeah, so we have, this is important remark. Now you can replace, instead of US alpha you can write U H alpha S alpha. Yeah, because S alpha does not vanish, H alpha S alpha does not vanish, so both of them represent the same open set. Yeah, so if you draw a polynomial, it will just cut exactly at 4 points, also for H alpha S alpha. Yeah, because H alpha S alpha, again, yeah, the open sets are precisely the same. Now we put new notation. So new notation, I will write new S alpha in this slight red color. This new S alpha will be the new denominator. Yeah, so instead of H alpha S alpha, we will write S alpha, and again for the numerator we will write G alpha again in place of G alpha S alpha. So we have these polynomials S alpha and G alpha, which we have just written in red. Yeah, one represents the denominator, another represents the numerator, and X is covered by all these X is covered by these sets US alpha. Yeah, so we are trying to cover X by these polynomials S alpha, which do not vanish on open sets. So you constructing open sets by taking complements of the places where polynomial S alpha vanishes. And F is equal to G alpha by S alpha. Yeah, because I've just replaced numerator and denominator. I've given them new notation. So that is why I'm writing it in red. So yeah, on US alpha. Okay. So till now we have not done much. Yeah, we have just drawn some figures and made things clear. Now this is the only critical part here. So X is covered by these two sets, and X so these two sets are complementary to each other. Yeah, so X is covered precisely by sets which sets such that S alpha X does not vanish, and so the space is divided into two parts. Yeah, where the polynomial S alpha X vanishes and where it does not vanish. Where it does not vanish, we have put it in X, and where it vanishes, we are taking it separately. Yeah, so where the S alpha X does not vanish, we are taking those sets, taking their union and forming space X. So if you take X on this space, what you get is a null set. Now this we are just going to rewrite it as this thing. So we have two complementary spaces. Yeah, one where S alpha X vanishes, and one which is formed precisely by those spaces where S alpha X does not vanish. So notice that I can write G alpha as F times S alpha. Yeah, this we are going to use in a minute. So that is why I'm writing. Yeah, so obviously you can multiply both sides with S alpha precisely because US alpha does not, on US alpha, S alpha does not vanish. Yeah, and both sides are 0 on X minus US alpha. Yeah, so again this is to highlight the point that X and X space is made up by all those open sets where this polynomial S alpha X does not vanish. Yeah, that is the definition of US. So again, yeah, so we are going to rewrite this. So first I will write the S alphas. You now apply null Stellensatz. Obviously you see the null set and you say, okay, null sets means it's going to, the vanishing set of whatever is equal to null set will generate 1. So what is the vanishing set? So you have all these S alphas which are equal to 0, and you have the set X which generates the ideal, of the affine algebraic set X. So you have seen set X is where these polynomials do not vanish, and it is taking the union of it, and then you have all the spaces where these polynomials vanish. So these are two complementary to each other. Yeah, so you have vanishing and non-vanishing. Yeah, so on X is again constructed by sets US alpha where S alpha does not vanish or is not equal to 0. That is the only idea in the entire thing. In the entire proof, that is the only idea. So now we write down it as P1, S1, P2, S2, where Si is a polynomial and Pi is a polynomial. Yeah, so that is how the first thing is to be interpreted. So you have to generate one, and you generate one like this. So now we take a regular function f, whatever was there on space X coming from U or expanding U or coming from collection of U's. You multiply left hand side this 1 by f, and then you multiply right hand side also by f, and you're done. Now f is obviously a polynomial. So we will just expand it out and write down the obvious. Yeah, so now you see G1, G was a polynomial because f times S1 is G1, f times S2 is G2, and f times SR is GR, and therefore f is a polynomial. because Pi is a polynomial. So the only thing we need to remember is that you have these elements, polynomials S alpha, which are equal to 0 and not equal to 0. Where there are not equal to 0, they correspond to ideal of X, and where they are equal to 0, that is the other space. Both of them generate 1, and once you have generation of 1, then you have a equation like P1 S1 plus P2 S2 plus PR SR generating 1, and then you just multiply by F and end of story.